Recording is rolling. Welcome to Tuesday, March 29. So we got these chapter 13 puzzles adapted from your book, and they're going to involve, well, these principles right here. Got ideal gas law on deck. There's Archimedes principle, Pascal's principle, Bernoulli principle. There's some thermal expansion questions. So we've gone over those last few days with the principles themselves, how to solve them. You guys seen some demos. Okay. Now we're going to solve these problems. Okay. So just like back with the chapter 12 problems on the other side of the same paper, I'll solve my version. You guys have the same stories, just different numbers. Number 79. Actually, these first two, just at a glance, you guys see, well, cylinder, piston, gas. Already I'm thinking that the first two questions are probably going to be some version of ideal gas law. Now, you guys remember ideal gas law is actually a composite of a few smaller laws that led to the point where there was Boyle's law and Gay-Lussac law and Charles law, right? That had to do with some kind of proportional relationship of pressure, volume, and temperature, right? Absolute temperature. So let's hop in. A constant pressure thermometer. Ooh, okay. So just from those first few words, we're already getting some hints about how to frame this question. So we know we're holding pressure constant, right? And okay, if it's some version of a thermometer, then we're allowed to have a change in temperature, right? See, it's made with a cylinder containing a piston that can move freely inside the cylinder. And so I got a diagram for that here. The pressure and the amount of gas are kept constant. Okay, so the pressure is constant, we did that already, but also the amount of gas. So that's a pretty good assumption too, right? I mean, it's like a sealed chamber or something like that. As the temperature changes, increases or decreases, the piston moves up or down. Okay. So if the cylinder's moved way up, we could say it's pretty warm. If it's moved down, it's pretty cold. All right. Oh, that's why this is a thermometer, like some version of that. And so now to the numbers. At 0 degrees Celsius, the height of the piston is 15 centimeters. What is the height of the piston at 100 degrees Celsius? Oh, right. So, now my numbers I know are different than your numbers, but at least my numbers, it looks like happen to be the boundary conditions for the for liquid water, right? As cold as liquid water can get and as hot as it can get, or it changes phase. Okay, so 79. Okay. I'm going to jot down an ideal gas law and we're going to navigate from there. So pressure times volume is equal to number of moles of gas times a constant R that ties everything together times the absolute temperature. Okay. Remember, anytime you're applying ideal gas law, which obviously we're about to do, the temperatures you plug in have to use an absolute scale, not a relative scale. Because if you use a relative scale, you could go negative, and that wouldn't make any sense. Right? If you double the temperature, well, you got to use an absolute scale. That's the only way to do that. Right now, we were told what do we know that's constant? R is obviously constant. I mean, it's literally a constant. Right? No, different numbers depending on what units you're working with, but that aside, we were told that the gas itself was kept constant, right? Some kind of sealed chamber, and also that the pressure was kept constant. It's a constant pressure situation. Ooh, so there's some relationship between this V and this T. I want to say this is Charles's law. I think that's what it was. Right? That volume is directly proportional to temperature. That's say if you double the temperature, all else constant, the corresponding volume would also double. Imagine if you have a balloon and heat up the balloon, you think the balloon's going to expand, cool it down, it's going to contract. Actually, Paul Hewitt did that. Remember, he brought in the liquid nitrogen, the whole thing, cool down balloon, cool down, it contracted. Ooh, that's like this. Right. So if we're going from one temperature to another temperature, and the corresponding volume is going to change, I'm thinking that this is going to lead to like two equations. So it's going to be some pressure times volume equals nRT for one scenario, and some PV equals nRT for a different scenario. Okay, so I'm going to start throwing on some subscripts. Let's do like a T1 and a V1 and a corresponding T2 and a V2, like that, right? Okay. So you guys see how this is set up for like some system of equations? Okay. Can I know this in terms of variables, but expand your imagination a little bit, think about how this solves in terms of variables, because we're looking for some kind of proportion. Is it okay? Can I take one equation and just divide it by the other equation and get something that's like a valid equation from that? I can do that, right? I remember in algebra, there's processes like substitution, elimination, and it's okay to do something like that. Take one equation and divide by the other equation. Now, if you do that, remember, we're keeping constant pressure. So, that P and that P have to be the same. Okay. Same thing for the R and also for the N, where N is the number of moles of gas. Okay. So I'm getting this relationship. The ratios of the volume after compared to before is the same thing as the ratios of the temperatures after compared to before. Again, this is a piece of ideal gas law. It's like Charles' law. Okay, so I bet if I have 3 of these 4 variables, I could solve for the 4th one. Okay. But what was the question again? What is the height of the piston? Now I didn't say what is the height of the piston. I'm going to do one more substitution. Okay, volume, guys. Would the volume of this thing be this cross-sectional area multiplied by the height? Is that okay? This cross-sectional area multiplied by this height represents the volume of the gas on the inside. Okay, I'm going to do that. So instead of V for volume, I'm going to say like cross-sectional area times height. And then I'll do that for both of these. Okay. Now it's the same cross-sectional area for, because all this piston's going to do, the cylinder is going to just move up and down, right? So area also cancels down. Okay, so it looks like the ratio of the heights also happens to be the ratio of the temperatures. All right. You possibly intuited that, right? Like if you double the temperature, it's going to like double the volume, therefore double the height or constant area. Okay. Now I think we can start plugging in numbers. So the first number I gave you was the cold temperature, and mine says 0 degrees Celsius. I should think everybody has 0 degrees Celsius. So that was the initial temperature. Should I plug in 0 right here? 0 degrees Celsius? Should I plug in 0? No? What should I plug in? Because if I did plug in 0, I would be dividing by 0. Might be a hint that something's wrong. Hold on a minute. I don't. 273? You guys like 273? Right? Because I need to plug in like a Kelvin value, right? See, if I'm taking a ratio of temperatures, here, let me give you guys a counterexample of why you would not want to plug in Celsius. I mean, we got here. If you go from 0 to 100 degrees, what is 100 divided by 0? Well, you can't calculate that. It's like undefined. Right? Yeah, we need Kelvin. So temperature 1, I'm going to plug in 0 degrees Celsius is the same thing as 273 Kelvin. Right? And temperature 2 is, well, you know the conversions, whatever it is in Celsius plus 273. So this is actually 0 plus 273. Okay? So my second temperature happened to be 100 degrees Celsius. So are you guys going to do 100 plus 270 or whatever the Celsius plus 273 Kelvin? Okay. So in my case, I'm going from 273 to 373, right? Okay, so there's some proportional increase of temperature, like the absolute temperature. Okay. And it's going to be the same proportional increase in height for that cylinder to move up down on that piston. Okay. And I know my initial height because that was also a given value. On my paper, it says 15 centimeters. For you guys, I think it's something else. You guys see how it's going to feed in like that? Okay. Now, one more mass step, I'm going to take that height, that original height, and cross multiply it up. So my height 2, therefore it's going to be my height 1. I've got a number for that, so just go ahead and plug that in here. Let's run out of paper. Times, I've got 373 Kelvin compared to 273 Kelvin. The units cancel, the Kelvin cancels. All right, and there it is. There's my second height, and that is an answer choice, so I am good with that. Okay, guys set? Yeah, let me give you guys a little time. All right, anybody stuck in need help? You guys good now? You guys got it? All right, ready for the next one? All right, here we go. Next question, which involves a pretty similar looking type picture. Oh, I remember, I was gonna say one more thing, because you're dropping the stuff anyway. The fact that height scales linearly with the temperature change. Ooh, that might be an indication of like a thermometer, like the number markers are also scaled linearly, right? So if you had a say the volume of some liquid inside changes, right? That'd be similar to that. Number 80. Okay, a piston with an area, cross-sectional area of 0.02 square meters. So that's the area of this circle right here. Encloses a constant amount of gas, just like the last one. There was a constant amount of gas in the cylinder with an initial volume of 0.67 cubic meters. So I'm giving you a volume this time, like the volume of gas. Now, that might change, but we're about to find out here. The initial pressure of the gas is 101,000 pascals. Okay, that happens to be atmospheric pressure. Okay. So that's what we're in right now in this room. A 150 kilogram mass is placed on the piston, which pushes the piston down. Okay, see that? Now, side thought here, let's think back to last semester. Even though I told you the mass of this thing in kilograms, you guys know mass is just like amount of inertia, amount of material. Isn't really a weight that actually provides the force to push us down, right? Which would be mass times gravity field, right? So I'm just thinking ahead a few steps here. Place on piston, pushes it down. Wouldn't that actually increase the pressure inside? Increase the pressure until maybe there's some kind of equilibrium, right? You got the weight pushing down and the pressure pushing back. Okay. Let's keep the temperature constant. I mean, sounds like a pretty good assumption. Okay. What's the new volume of gas in the cylinder? Huh. Okay, so what I'm thinking is that there's going to be pressure changes and some corresponding volume change. You might call this Boyle's law, if you like Boyle's law. But what I'll do is go back to ideal gas law and then derive Boyle's law from that, and then we'll go on from there. So kind of like I did the last one. So some version of PV equals nRT. Right? There's ideal gas law. Okay. Now I remember what we did last time was we took that, set up like two equations, and then canceled out everything that was constant as divide one by the other. We do a very similar thing right here. So I'll set up another PV equals nRT. And say, okay, well, what's constant, and what do you put subscripts on, which would indicate some kind of change? Okay. Well, we're keeping R is obviously constant. The number of gas molecules, that's constant, and we're also keeping temperature approximately constant. So it looks like everything on the right side is just the same, right? But the left side, I'm getting two different pressures and two different corresponding volumes, right? Okay. So here's my system right here. Well, say system of equations, but those are sort of formulaic, okay, in terms of variables. And we'll do the same method that we did last time. So I'll divide one equation by the other equation and get this ratio is equal to, you guys see this is going to be 1. Okay, so P2V2 over P1V1 is all equal to just 1. This all becomes 1, right? Then I can take P1V1, cross multiply it up, and I get P2V2 equals P1V1. This right here actually is Boyle's law. All right. Now, what do I know that I could plug in? I did give you guys an initial volume. That might be like V1. I did give you the initial pressure. That's like this P1. And what about for P2? Well, I did give you a mass that you could get a weight from. So maybe do some version of that. And I guess we're trying to solve for, we're trying to solve for V2. What's the new volume of the gas? So we're like trying to solve for that, right? Okay. All right. So in terms of variables, V2 would just be V1 multiplied by P1 on P2. Say something like that, right? Gave you V1, gave you P1. What about this, the second pressure, P2? Okay. I bet the second pressure, because the initial pressure probably would have been atmospheric pressure. Yeah, atmospheric pressure. Oops, I changed my voice out. Inside the container, but also atmospheric pressure pushing from above. Right, they're both 101,000 pascals. Right. And that weight that I put on top of that, well, that's just going to increase the pressure even more. Okay, so V2. Let's slide everything to the left here, and give myself a little space because that's the bigger expression is the initial volume multiplied by, okay. See, the initial pressure divided by the new pressure. Now the new pressure is going to be the initial pressure, like atmospheric pressure, plus, okay, remember there's a weight acting on top, right? Like pushing down, so it's like an increased force. Okay. So wouldn't that be the weight mg, but divide by something, okay? Guys, weight, what's the unit for weight? What do we measure weight in?
Grams.
Let's see, grams or kilograms is mass. Mass times gravity, we're gonna measure in newtons, right? Yeah, newtons for force, okay? But pressure, that's in pascals, right? So guys, can you add newtons to pascals? No. So if you're looking for an increased pressure, this weight is acting on what that would result in some kind of pressure? What is pressure? Force divided by. How about this? You guys pump up your bike tires, use an American pump, says PSI. What does PSI stand for?
Pressure per square inch.
Pounds per square inch. That's what pressure is, right? Pounds per square inch. Ah, it's not some kind of force per unit area. I need to divide by area. You guys see that? Right. And I told you what that area was. That was the first number I gave you right here. Ah, I told you with it. Okay, so I don't know. I could approach this a little bit differently, but this weight, which is m times g, divided by this cross-sectional area, results in like an increased pressure, right? On top of the original atmospheric pressure, right? And this is compared to the original pressure. All right, that's in terms of variables. So let's go ahead and pop in some numbers. So my original volume was 0.67 cubic meters. So we take that, multiply by this ratio. You guys see the fact that the denominator has to be greater than the numerator means that this ratio is less than 1, which means that it's a shrinking volume. But that makes sense because if you put a weight on top, it's going to push it down and decrease the volume. You guys see how this checks out? Okay. That's the bigger picture that I want you guys to see, be able to get out of the class like this. Like, well, how do these variables tell that type story? If you increase this, that causes that to decrease. So the original pressure was 101,000 pascals, atmospheric pressure. Okay. And then the new pressure would be 101,000 pascals plus the weight. Now it's mass times gravity field. So my mass was 150 kilograms. So mass in kilograms times 9.8 meters per second squared. So that'd be gravity field. Okay. All divided by cross-sectional area was 0.02 square meters. Okay. So the old pressure plus the change in pressure is the new pressure. Okay. Let's try this out. Yeah, that is an answer choice. So if you do it right, then you should get a new volume that's smaller than the old volume, right? Just like the picture shows, you put a weight on, it's going to compress that mass of gas and result in a smaller volume. You guys got that? Anybody need help? You guys ready for the next one? All right, next one. Number 84. An antique yellow statuette of a bird is suspended from a spring scale. Okay, so we're gonna pick something up with a spring scale and we're gonna weigh it, and it weighs some number of newtons. What you guys just told me, weight is measured in newtons, so there you go. Okay. When it's suspended in air, right? So air, maybe there's a tiny buoyant force, but basically negligible, right? But when you submerge this thing in water, now the spring scale reads not as much, right? Because now there's like a supportive buoyant force, so the spring scale doesn't read as much. Okay. Hey, this sounds a lot like what we did back on Friday, doesn't it? You guys remember I gave you a beaker of water and like this glass prism piece, and then you hooked it with the tape and then submerged it, reading different spring scale forces. Okay. And what is the question here? What what material is the statuette made of? Oh, and all the answer choices have different materials corresponding to what with different corresponding densities, because each density would be associated with some material, or say each material associated with some density. This is exactly what we did back on Friday. In fact, you know what? I have the notes right here. But there was a whole process we went through. You guys remember we did this back on Friday? We were trying to figure out what's the density of that object, right? The whole deal. Right. Now, one way you could do it is submerge it, say what's the change in volume of the water that represents the volume of the object, and take the mass of the object, divide by that volume, that could be the density, right? But how can you get it without seeing the volume change? Because maybe the beaker is like, what if this is a really big beaker? So it's really hard to get an accurate volume change. You can get it just from the scale. And we went through the process. Here's what we do. I'll just do this from scratch in front of you guys with just the numbers on this paper. And then at the end of this, we're going to flip to the end of these notes. And we'll look at the formula I derived just in terms of the scale readings and see if it ends up being the same thing. Okay. So just only give you two numbers here, two force readings. So number 84. Let's go beaker of water here. Let's get the statuette of a bird. And we're gonna hook this thing with a spring scale. Right, now I'm thinking about free body diagram on this statuette, this bird statuette, free body diagram. Let's do that. Okay. So I'm thinking there are three forces on this bird submerged in the water. It's got its own weight. I'll label that mg because I've been calling it mg since last semester, so I'll just stick with that for the weight. Okay. Now, if you were hanging this in the air, then the spring scale reading would be pretty much that number. There's a buoyant force on the bird acting upward. So F sub B for buoyant force. And there's also a force from the spring scale, F sub S, force from the spring scale when it's submerged. Right. So in my notes, in the next couple pages here, when I do F sub S, I'm referring to this force, the force on the spring scale when the bird is submerged in the water. Okay. Okay. Now, since this would be an equilibrium, right, the bird's not accelerating up or down, there's no net force. Oh, we change this out. Change out this headset. Okay. I know that those three forces have to balance to 0 newtons. I can say some version of this. Some of the forces vertical equals 0 newtons. Therefore, couldn't you say that this buoyant force is the difference between these two forces, right? So therefore, buoyant force is equal to the full weight of the bird minus the spring force when it's submerged. Right? And I like this expression because these are the two numbers that I gave you. I gave you the weight of the bird, and I gave you the spring scale force when it was submerged, right? You have these two numbers. Let's go ahead and get that right now. I'll just one just piece by piece. So 11.8 newtons versus 7.43 newtons. So this is my 11.80 newtons. This is my 7.43 newtons. Subtract those two, and I'll get what the buoyant force is on that bird. That is 4.37 newtons. Right? And do you guys find your own buoyant force too? Okay. Nah, that's not the answer yet. That's just one step. Does everybody know the buoyant force on their bird statuette? Because you just take the difference between these two forces, right? Like that. So get over here. Right. Now let's bring in Archimedes' principle. You guys remember Archimedes, the guy who was trying to basically solve this problem with the gold crown, and or was it really gold? Right? And he has this revelation as he's in the tub and shouts Eureka, runs naked through the streets. That guy, he figured out that the buoyant force is equal to the weight of the water displaced, weight of the displaced water. And you can break that down in formulas like this: density of water times gravity field times volume displaced. Okay, now why is that the case? Well, because density of water times the displaced volume, that represents the mass of water, right? Density times volume is mass, times gravity field represents, oh, the weight of the water displaced. That is the weight of water displaced. This is Archimedes' principle, right? Archimedes, right here, Archimedes' principle. Okay? And we know some of these values. Like you guys know the density of water is a flat, even 1,000 kilogram per cubic meter and base SI units, right? Because metric system. properties of water. You guys know that gravity field is 9.8 meters per second squared. And you know what the buoyant force is because we just found it. It's this many newtons. Many newtons of force is equal to this times V displaced. Okay. Now V displaced, that's again, not exactly what we're solving for, but it is an important step. So let's do this. You guys see me take the 1,000 and 9.8 and just divide those down. So it's 4.37 divided by 9.8 and then divided by 1,000. I'm getting V displaced is equal to, it should be a tiny, tiny, tiny number of cubic meters. Okay. Which makes sense. I mean, if you're talking about a statuette of a bird, right, and you're dunking it in a beaker of water, okay. You guys know 1 cubic meter, that's a little bit more than 3-4 tiles by 3-4 tiles by 3-4 tiles. If I had like a big old box right here, right, so like a big old box, I filled up with water, right, yeah, like 1,000 kilograms. Right? But think about that huge volume, right? Right. So yeah, the statuette is a tiny, tiny, tiny fraction of that, which makes sense. Checks out. Right? You guys get that? You guys figure out the volume of your bird? That's also the volume of the bird, right? All right. Next step. It's going to be a multi-part process. Okay. What we're actually interested in was what is the density of that statue? So I'll say density of the bird statue. Okay. And wouldn't that be the mass of the bird statue divided by the volume of the bird statue? Right? The temperature? Okay. And we're almost there. We almost have those. We actually do have the volume of the bird. That's this volume right here. So this feeds in right there. Right. But the mass of the bird, we almost have it, not quite, because I did give you the weight of the bird in newtons. That's how do you go from weight back to mass? You divide by what? Gravity field. Yeah. You guys remember how weight is equal to mass times gravity field? So if you just want the mass part, shouldn't you just take this full weight and divide by this G? Okay, so I'm going to do the weight of the bird divided by G, which is 9.8 meters per second squared. Okay, let's put it all together. Density bird is equal to, okay, I'm going to take the weight of my, now the weight of my bird was 11.8 newtons, so that's the higher force rating, 11.8 newtons, divide by 9.8 meters per second squared. That represents the mass of the bird. Then divide that by the volume of the bird, which is this number right here. Okay. And that's going to give me kilogram per cubic meter. Let's see what this is. And end up with some kilogram per cubic meter. If you like, especially if you're, say, a chemist, you might want to do gram per cubic centimeter instead. And for that, just roll the decimal back 3 places. So I'm getting 2,700 kilogram per cubic meter. I might call it 2.7 gram per cubic centimeter. Right. But that happens to exactly align with the material aluminum. Okay, so I have an aluminum bird. Right? Now, you guys may or may not have aluminum bird. You might have a zinc bird, you might have a silver bird, you might have a gold bird. Okay, but you will end up with one of those. Okay. I'm gonna here. I said I was gonna do this another way, so let me break out the notes back on Friday and try with this other method. So here's what we did back on Friday. We solved the same problem, but just in terms of variables. Okay, here we go. So looks like if I do the hanging weight in air divided by the buoyant force, which is just the difference between the hanging weight and submerged force, okay, and then multiply that all by the density of water. Right, this is what we did back on Friday. This is the end result. I should get the same thing. Let's see if I did. Let's see if I did. So I'm going to plug in my 11.8 newtons right here, 11.8 newtons divided by, open parenthesis, 11.8 newtons minus 7.43 newtons. Okay. Then take this and multiply it all by the density of water, which is 1,000 kilogram per cubic meter. Yep, it's the exact same thing. There's aluminum right there. There's the density of aluminum. Get the same thing. Okay, yeah, so I gave you two force ratings, right? Okay, so take the weight, which is the larger force rating, divide that by the difference between those two force ratings. The difference represents the buoyant force. Okay, right. And once you got that ratio, multiply by the density of water is an even 1,000 kilogram per cubic meter. Okay. Right. So pretty much just this right here. Okay, and you will get one of those answer choices, which corresponds to some material. One of those materials. How many of you guys got the Goldberg? Goldberg. Oh, look at you guys, the Goldbergs. Yeah. Some of you guys got. You guys ready for the next one? At number 87. What is the apparent weight of a rock submerged in water if the rock weighs, say, 45 newtons, for example, in air and has a volume of, should be a tiny volume, 2.2 times 10 to the -3 cubic meters? So I want to draw this out. Look at free body diagram of we're looking at 87. So there's this rock, but let's say it's sitting at the bottom of a beaker full of water. Water levels will do. Okay. Let me think about free body diagram on this because that might help give some context here. This rock has a weight pulling straight down. That's mg. And I'm thinking of two upward forces. There's a buoyant force, maybe like this, F sub B. Okay. And there's also a normal force from the bottom of the container, F sub N. Now, the bottom of the container, if you put a scale down there, ooh, like it's weighing it, wouldn't that scale actually read the normal force? And wouldn't that represent the apparent weight? Like you guys know if you jump in the swimming pool, your apparent weight should be, well, it should be about 0 if you're just like floating, right? But a rock, okay, it's going to sink to the bottom. There will be some normal force, right? And that's what we're solving for. So wouldn't the normal force be equal to the difference of the weight and the buoyant force? Pretty similar to what we did before, because this right here, sum of forces has to go to 0 newtons for equilibrium, right? Okay. So we're looking at this. Okay. What did I get? Oh, actually, I told you this number right here. I told you how many newtons that was. Okay. Now, buoyant force, so this right here was given. I'll just make a note of that. Buoyant force, isn't that equal to rho GV, Archimedes principle? Density of water, not density of the rock, but density of water, times gravity field times volume displaced, which would be the volume of the rock because the entire thing submerged, sunk to the bottom. But, all right, we got this. Normal force then, which is again the apparent weight, that's equal to the weight in the air, which for me was 45 newtons, minus density of water is 1,000 kilogram per cubic meter. Gravity field was 9.8 meters per second squared. And the submerged volume was 2.2 times 10 to the -3 cubic meters. Oh, other way. By the way, 10 to the -3 and 1,000 cancel out exactly. So save yourself the calculation. I'm looking at this many newtons right here. That's the normal force from the bottom, which would also represent the apparent weight of that rock. It's going to appear to not weigh as much because it's submerged in water. There's a buoyant force on it. That's working out for you guys? All good? You guys ready for the next one? All right, next one. Number 90. Suppose the density of salt water is a bit more than 1,000 kilogram per cubic meter, and the density of ice is a bit less than 1,000 kilogram per cubic meter. Okay. Now, it made everybody's numbers a little bit different, but I try to keep it kind of realistic. Okay. What percentage of the volume of a floating iceberg is submerged? Ooh, you know what? I bet before we even start this one, most of you guys might know the answer to this. Because if you see an iceberg floating in the ocean, how much of it is over the water line? What about 10% maybe? You guys ever heard that? You see an iceberg, you're actually seeing the top 10%, and the other 90% would be submerged. Okay. You guys think the answer is probably going to be whatever's closest to 90%? Okay. Okay, now how can we figure this out systematically though? Yeah, systematically. Okay. Well, let's draw an iceberg and do a free body diagram, and then work away from there. Okay. So you got a water level. Oh, zoom out here. Iceberg. So maybe I have an iceberg, something else out like this, floating around. I should say too, if you Google iceberg and you find any kind of animation drawing, they always show them like upright, which is not really stable. So it's probably closer to being stable. So center mass of this iceberg, what are the forces on the sky? Well, I know there's a weight pulling it down. That's the mass of the ice times the gravity field. That would represent the weight. Yeah, let's go down to the bottom of the ocean. And then what's keeping it up is a buoyant force, F sub B. And Archimedes' principle says that's equal to the density of the water times gravity field times the volume displaced. Okay. Now, volume displaced, isn't that just this hatched part right here? Just that hatched volume? Like anything over the ocean surface, it's not displacing water, just this part underneath the ocean is displacing water. Right, so if the sum of the forces has to be 0 newtons, then couldn't I say that each of those is equivalent to each other in magnitude? Right? So that the mass of the ice times gravity field, so the weight of the iceberg, is equivalent to the buoyant force, which is density of the water times gravity field times displaced volume. Okay. Those have to be equal. You know, you guys remember, okay, Archimedes' principle, it really says the weight of displaced water is what is equivalent to the buoyant force, right, the magnitude, and that's density times volume is mass, right? And then times gravity field is weight. Okay. So could I sort of like take the mass of the iceberg and break it up in terms of its own density and volume? I mean, I did give you the density of ice. That might be good to be able to somehow feed into this formula. I'm going to take the mass of the ice and say the mass of the ice is density of ice times the volume of the entire iceberg. Would that be true? Say just a little substitution right here for the mass of the ice, density times volume of the ice. Okay. All right, now we've got densities, gravity fields, volumes. What's going to cancel out on both sides? The gravity field. Isn't that the only thing it cancels out? Because different densities, different volumes that we're talking about, gravity field is the same. Actually, it's a good thing that the gravity field does cancel out, because what that means is if you took this whole experiment up to, say, Mars and had like a iceberg floating on Mars, that proportionally the same, but the same proportion of it would be submerged, right? It kind of makes sense. So we're talking about densities and material properties. Okay. Now the actual question is, what percentage is submerged? Percentage submerged, isn't that displaced volume compared to the entire volume of the iceberg? Okay. So if I divide this down, see, V displaced compared to V of the entire iceberg, and then divide the other way, that'd be density of the ice divided by density of the water. Okay. And actually, that's exactly what's being asked. Right? What proportion is submerged? And this is set up to solve that. Right? You're not. Oh, I should have said from the outset, you're not actually solving for any one of these variables specifically. You're solving for a ratio of those two volumes, right? Displaced compared to the entire thing. That makes sense. That would tell you the percent of submerged. Okay. So it ends up at the end of the process just being the ratio of the densities. So I'm looking at what did I say for density of ice on my paper says 910 kilogram per cubic meter. I think it's pretty close to the true value. Maybe not exactly, but maybe my ice has like, I don't know, things mixed in with it, maybe air mixed in with it or dirt mixed in with it, throws off a little bit. Okay, and then seawater, well, it depends how salty the water is, so probably plus or minus factor on that too. And then, oh, guys, if you want to turn this into a percentage, then technically the last step is to multiply by what? Yeah, 100%. There you go. Because this might be like some proportion like 0.88, and then multiply by 100, get like 88%. I think it's how this turns out. 910 over 1025. And then times 100%. Yeah, I'm looking at 88.8% for my iceberg is submerged. So the other 11.2% would be above water. There you go. Yeah. Yeah, let's see chat. 89. All right, you guys got the iceberg question? It's good. Okay, next one. Number 93. Let's zoom in here. How much longer will a 300-meter long steel bridge be on a 30°C day in August? It's a pretty hot day right there, compared to a 5°C night in January. Okay, so got a hot day in August compared to a cold night in January. Okay. Oh, this has to do with thermal expansion. There's the coefficient of thermal expansion for steel. One of these posters hanging from a ceiling. This one right here talks about thermal expansion. 300-meter long bridge. That's pretty comparable to the causeways we have connecting our islands around here. Number 93. So we got this bridge. This here. It had some original length. I'll call L naught. Okay. And then say if this heats up, it might expand out to like out here, for example. I'm gonna exaggerate my picture, but you guys get the idea. Where there's some change in length, I call it like delta L. Change in length. Right? And that delta L change in length is equal to the original length multiplied by coefficient of thermal expansion multiplied by the change in temperature. Okay, that'll be true. So I told you the original length of the bridge. Mine was 300 meters long. I told you coefficient of thermal expansion for steel, this is like a steel bridge. That's 12 times 10 to the -6. And the unit for that is per kelvins, like 1/K, 1 kelvins. And then the temperature change. Well, I went from 5 degrees to 30 degrees. Can I do this? Can I say 30 degrees minus 5 degrees? Can I just subtract the Celsius one from the other? That's okay. And the reason that's okay is because a temperature change in Celsius is the exact same temperature change in Kelvin, because Celsius and Kelvin are scaled the same. Like a change of 1 degree Celsius is a change of 1 Kelvin. Okay. Now, if you were to multiply directly by temperature, you'd have to convert to Kelvin first, but in this case, you don't really have to. Okay, so what do I get here? 300 times 12 times 10 to the -6, all times 25. I'm looking at 0.090 meters. Okay. Now, 0.09 meters, I could also call that 9 centimeters or 90 millimeters. So now our causeway is connected to our islands around here, probably mostly concrete, but you guys remember how concrete and steel have the same coefficient of thermal expansion? That's what allows for steel reinforced concrete. Okay. So I bet between a really cold winter day and a really hot summer day, I bet the expansion of our own bridge is probably pretty comparable to the numbers right on this paper, which is about that length right there. Great. Is that working out for you guys too? Okay, next question is also thermal expansion, but it's in 3 dimensions because it's talking about a volumetric change, but we're gonna have to save that one for tomorrow because we're running up against the bell here. So we'll hit a pause point here and solve the rest of these tomorrow.